Hello my dear student. Now let us discuss about the fact that every non-empty perfect subset of R is uncountable. This is a general result. If there exists a non-empty perfect subset of R, that subset is uncountable. So last time we have discussed that a Cantor set is perfect, it is non-empty, it is closed, it is compact, it is totally disconnected. Those things we have discussed last time. So now we are going to prove a general result that every non-empty perfect subset of R is uncountable. So since Cantor set is non-empty perfect subset of R, it is going to be uncountable, and that is the main objective of this lecture. Cantor set is uncountable. Okay, and lastly we will prove that the Lebesgue measure of Cantor set is 0. That means we want to find out an example of an uncountable set whose Lebesgue measure is 0. So Cantor set is the right candidate for the example. So in order to show that one, we have done that. Cantor set is perfect, it is non-empty, it is closed, it is compact. Now let us show that Cantor set is uncountable. Okay, so we will achieve that goal by proving the general result that every non-empty perfect set of R is uncountable. We are going to use the method of contradiction here. So everyone knows that what is method of contradiction. We are going to assume the fact that we are going to assume that E is countable, and we will arrive to a contradiction. Okay, first let us assume that E is a non-empty perfect subset of R. Also E is countable. This is our assumption, and let us arrive to a contradiction. Then our assumption is wrong. Therefore E must be not countable. Okay, so then by definition of countability, what is that? The member of E can be enumerated as a sequence. The member of E, all member of E can be enumerated as a sequence. That means, so the first element is x1, the second element is x2, x3, x4, x5 as a sequence. Every member of E is also member of the sequence. So there is no member of E left out which is not in the sequence. Okay, so E may be enumerated as a sequence, and let that sequence be xn. This sequence like xn. That means E is equal to this sequence. Every member of the E is a member of this sequence. Every member of this sequence is also a member of E. They are equal. Okay, so this is quite possible by our assumption that E is countable. And then from this countable set E, we are going to form another sequence called yn. So that is the crux of this problem. If you understand how to construct this sequence, then you will understand the theorem completely. So be careful and listen carefully. If you don't understand something, you can call me back in my mobile number. So for this tutorial, you can listen to the video carefully. I will explain line by line how we construct the sequence yn from the set E. Okay, so let us do it inductively. Let us do it by inductive method as follows. First, the first member y1 is equal to x1. Okay, the first member of this sequence is equal to x1, so which is the first member of this sequence. Okay, and then the second member of the sequence, new sequence, is equal to x2. So x2 is what? X2 is the second member of this sequence, which is exactly equal to with this E. All right, so now we have determined the first and the second element of this new sequence yn. Then let us take a small positive number. Small means it is less than 1. Okay, so that say x1 and x2 are two different elements, so x1 minus x2 is never 0. It is if you take a modulus, then it is a positive small number. Then we choose epsilon 1, the small number, in such a way that epsilon 1 is strictly less than the difference between x1 and x2. That is quite possible. This is non-zero positive number. Then we can take epsilon 1, which is strictly less than x1 minus x2 modulus. So then, if you think about an open ball center at x2, a radius epsilon. So suppose x2 is here and x1 is here, their distance is this much, okay? And then you take epsilon 1, which is less than between distance between x2 and x1. Then construct one open ball center at x2 and whose radius is epsilon 1. Then ball will be like this. So from the diagram you can see it that x1 is outside the open ball. Okay, so by our choice of epsilon 1, then x1 is not member of this open ball. Ball center at x2, radius epsilon 1. Okay, so this is our first construction. x1 is not a member of this open ball. What is x1? By our construction, x1 is equal to y1. That means y1 is not member of this open ball. Okay, so x2 is y2. All right, so this is an open ball. Okay, now let us use the fact that our set E is perfect. Okay, perfect means every member of the set is a limit point of the set itself. That is the definition of perfect set. Let me repeat again. What is a perfect set? Every member of the set is also a limit point of the set itself. Okay, so x2 is a member of E, therefore x2 is a limit point of E. Okay, then this epsilon 1, we can make it further, smaller. Epsilon 1 sufficiently small so that x3 is not a member of this open ball again. All right, so that means suppose x3 is here, suppose x3 is here. All right, suppose x3 is here, then what you can do is that you can make it epsilon 1 smaller than, so that the point x3 is excluded from this open ball. Okay, so that you can do it. So what do? You take epsilon 1 in such a way that it is less than the distance between x1 and x2. And next, what do? Again, you make it much smaller, that so that in the open ball center at x2 with radius epsilon 1, x3 is not a member. Okay, that you can do it. That is quite possible. Then let us use the fact that E is a perfect set. Since E is a perfect set, x2 is a limit point of E. Therefore, by the definition of limit point, every open ball centered at x2 with radius epsilon 1, every open ball contains some other member of E. Okay, some other member of E. All right, so there are lots of member of E. In fact, let us just take one of the members. Okay, and let us name that member y3, right? So this is how we find out, how we construct the third member of the new sequence. All right, the third member of this new sequence. We have already found out the first member and second member. How we find out the third member of the sequence is just now I have explained you. y3, that is a member of this open ball. This is possible because why? E is a perfect set. Right, and then what we do next, take another small number. All right, take another small number, epsilon 2. Let us call it epsilon 2, that is less than half of the first small number epsilon 1. First small number epsilon 1. Okay, epsilon 2 is less than epsilon 1 by 2, and it is also positive, greater than 0. All right, so that since this is an open ball, from the definition of open ball, what we have is that So suppose every member in this open ball, you can construct another open ball center at that point with suitable member, and that open ball is entirely within the first open ball. So this is open ball. By the definition of open ball, this y3 is a member of this open ball. Then we can take epsilon 2 so small so that ball of radius epsilon 2 center at y3 is lying entirely within this open ball. That is quite possible. Every one of you understand that from a basic topology, that is quite possible. Okay. Then what we have? x1, x2, x3 is not a member of this new open ball, right? x1 is not a member of this open ball, all right? x1 is not a member of this open ball, but this open ball is a subset of this open ball. Therefore xy cannot be here also, right? x1 cannot be here also. Okay. So, and then you choose epsilon 2 so small so that x2 is also not in this open ball. That is quite possible. x2 is also not in this open ball. That is quite possible. And then by our construction of the first open ball, x3 is not member of this open ball, and this one is a subset of this open ball. So x3, this x3 is also not a member of this one. Therefore x1, x2, x3 is not a member of this open ball. Okay, that is quite possible. That is possible thing to do. Okay, so you can choose epsilon 2 so small, smaller than the half of the first epsilon 1, so small so that x2 is not here. All right, x2 is not here. So that is possible. Let me draw a diagram here. Suppose this is your first open ball. Suppose this is your x1, x2 here, and y3 will be here. This is y3. Then this y3 is going to be the center of the second open ball, and now we want to determine the radius of this open ball. This is your x2. Then deliberately you can take open ball with suitable radius epsilon 2 that is less than the half of the first radius epsilon 1, and then this is a new open ball. Okay, my drawing is not very good, but you can understand what I mean. Then this x2 is not in the new open ball. This is the ball of radius epsilon 2 and center at a point y3. Okay, this is x2. So x2 is not inside this open ball. Okay, so what is the central idea? Now you construct this second open ball center at y3 and a radius epsilon 2, and so that x1, x2, all these 3 points are not in this open ball, and this open ball is precisely subset of the first open ball. Okay, so these are the steps. We have find out y3, the third element of the sequence. Now again by perfectness of the set E, we can take another member y4 to E. All right, so what is the perfectness? Again, let me explain you here. So this is y3 is what? Y3 is an element of E. E is a perfect. So now an open ball center at y3 radius epsilon 2, it is an open ball. So y3, since E is a perfect set, y3 is a limit point of E. So therefore the open ball center at y3 radius E2 epsilon 2 should contain many points of E again. Okay, it should contain many points of E. There are lots of points of E here. So out of those points, let us just take out randomly one point. Let us call it y4. Okay, Let us call it y4. So E is there, y4 is there, let us call it y4. So this is how we construct the fourth element of the new sequence yn. Okay, so y4 will be there. All right, so y4 is a member of this open ball. And then next, take epsilon 3, which is less than the half of the epsilon 2. Okay, and then by our construction, epsilon 3 is less than epsilon 1 by 2 square. Okay, so epsilon 3 is what? Epsilon 3 is less than epsilon 1 by 2 square. So then you choose like in the previous explanation what I have explained, you can choose epsilon 3 in such a way that new ball center at y4 with radius, this epsilon 3 is lying entirely within the second open ball like this. Okay, second open ball. So this is quite possible. Why? Because this is an open ball. That is coming from the definition of open set in topology. Okay, all right. Again, you can adjust epsilon 2. You can make it so small so that x4 is not there. Okay, x4 is not in this open ball. Open ball of radius epsilon 3 center at y4. So you can make epsilon 3 so small so that x4 is not in this new open ball. Okay, so then what we have earlier, up to x1, x2, x3 is not in the second open ball. Okay, here x1, x2, x3 is not in the second open ball, and then third open ball we construct like that. Third open ball is entirely lying within the second open ball. Okay, so since second open ball doesn't contain x1, x2, x3, third open ball also does not contain the points x1, x2, x3. And one more further condition is that in the third open ball x4 is excluded. X4 is not there. This is possible. Why? Because this is open ball. Okay, so in totality in the third open ball, how many points are not there of the first sequence? x1 is not there, x2 also not there, x3 also not there, x4 also not there. Okay, this is how we construct the third open ball centered at y4 and radius epsilon 3. All right, so I hope everyone understand till now. If you have some confusion, you can call me. Okay, I will explain you again. So this process we can process we can continue inductively. We can continue by induction. We can get we can find out the fifth member of the sequence y5, sixth member of the sequence y6, like this, so on, and we can get the fourth member of the open ball, fifth member of the open ball, like this. So how we construct the open ball? First open ball contain the second open ball, second open ball contain the third open ball, third open ball contain the fourth open ball, like this. Okay, so center of each open balls is the member of the new sequence. Okay, this is how we construct the sequence and the open balls. All right, so by induction we will get the sequence yn. So what is the central idea of the construction of the open ball? xn will not be member of the open ball center at yn and a radius epsilon n minus 1. Okay, all right, by our construction xn is not a member of the open ball center at yn, radius epsilon n minus 1. So what is the estimate of the radius epsilon n minus 1? Radius epsilon n minus 1 is strictly less than epsilon 1 by 2 to the power n minus 2. Okay, this is what. So here n is greater than or equal to 2, and this n is greater than or equal to 2. Okay, xn is not a member of this open ball. So this is coming from our construction. All right, in the third open ball, deliberately we did not include the x3 member of the first sequence, like that. Also what we have is that the nth open ball center at yn, radius epsilon n minus 1 is a subset of the previous open ball, that is ball center at yn minus 1 and radius epsilon n minus 2. So you have a sequence of open ball the first one contain the second, second one contain the third, third one contain the fourth, like this. Okay. So and then each open ball, you know, the xn is not a member of the open ball center at yn, radius epsilon n minus 1, and this epsilon n minus 1 estimate is like that. It is strictly less than epsilon 1 divided by 2 to the power n minus 2. So this is, so far this is the construction. Okay. And then next we saw that this sequence, all right, is a Cauchy sequence. You know, everyone knows what is a Cauchy sequence. For a given epsilon, there exists a positive integer n, capital N, such that for all nm greater than or equal to capital N, distance between yn and ym is less than epsilon hyphenatra. So that is the definition of Cauchy sequence. Okay. So let us now prove that yn is a Cauchy sequence. Let epsilon be an arbitrary small number. You take any arbitrary small number epsilon. So we know that, you know, let us see first. This is epsilon 1. It is keep on dividing by power of 2. So as n tends to infinity, you know, this sequence, you know, tends to 0. Right. As n tends to infinity, this sequence tends to 0. Then when epsilon 1 by 2 to the power n minus 2 tends to 0 as n tends to infinity. So there exists a positive integer n which is greater than or equal to 3, such that, you know, epsilon 1 divided by 2 to the power n minus 2 is less than or equal to epsilon. Okay. So this epsilon is used arbitrarily, so a small number. But this, since this sequence is tending towards 0, okay, after some stage, yeah, you can make it smaller than this epsilon, right? Because this is going towards 0, so you can make it smaller than any small number. All right. So there exists some positive integer that will be greater than or equal to capital N, such that this is less than epsilon. That is quite possible because this sequence is tending towards 0 as n tends to infinity. So then from our construction of the open balls, it is obvious that for all m greater than or equal to n, if m is greater than or equal to n, ym will be a member of open ball at center yn, okay, and a radius epsilon n minus 1. All right. If this m is greater than this n, then this ym is a member of this open ball. This is from our construction. You can see it because the first open ball contains second open ball. All right. So every member of the second open ball is a member of the first open ball, like that. Okay. So because of that, ym is a member of, you know, ball centered at yn, radius epsilon n minus 1, provided m is greater than or equal to n. This is true. So then this ym is a member of this open ball. That means what? From the definition of open ball, distance between ym and this yn is less than the radius of the open ball. Okay. So distance between ym and yn is strictly less than the radius of the open ball, because this is a center, na? This is a member of the open ball. So their difference is less than epsilon n minus 1. But we know that what is if the estimate of epsilon n minus 1, estimate of epsilon n minus 1 is strictly less than epsilon 1 divided by 2 to the power n minus 2. But 2 to the power epsilon 1 by 2 to the power n minus 2 is less than or equal to epsilon. Okay, that is distance between ym and yn is strictly less than epsilon for all m greater than or equal to n. So from this, what we conclude is that the new sequence we construct is a Cauchy sequence. So we have proved that the new sequence yn is a Cauchy sequence. All right. So this is a Cauchy sequence. So since E is a perfect set, any sequence inside E should converge, you know, to a point in E again. That is a property, because E is a perfect set and the new sequence is a Cauchy sequence, so it should converge. The Cauchy sequence should converge to a point in E because E is a perfect set. Okay, so the Cauchy sequence converges to a point. Let us call the point of conversion as y0. Okay, so then y0 should be a member of E. Okay, so this sequence should converge to a point y naught, and that y naught must be a point of E. Okay, so that is why n converges to what? Point y naught as n tends to infinity, and this y naught is a point of E. That is coming from the property of perfect set. So then what? Yn tends toward y naught as n tends to infinity. All right. So see, the thing is like that: first ball contains second ball, then every member of the second ball is a member of first ball, right? So then third ball contains the second ball, the fourth ball contains third ball, like that, no? So as n tends to infinity, you will get a smallest ball, right? The smallest ball is subset of every other previous open ball. Okay, and in that smallest open ball, your y naught is there. All right, so that means what? Y naught is a member of is open ball. The last ball will be the in the infinity. Okay, there is no last ball, but you can you can try to convince yourself that there will be the smallest ball in the last. That means as n tends to infinity, in that ball the limit y naught will be there. Okay, so that is the last ball, so that is a subset of is open ball. Okay, and therefore y naught is a member of is open ball. The limit y naught of the new Cauchy sequence yn is a member of is open ball. That is quite obvious. Okay, that is quite obvious. All right, so then x1 is not a member of the first open ball by our construction. X1 is not a member of first open ball, but y naught is in the first open ball also. Therefore x1 cannot be equal to y naught. Okay, all right, so x1 is not equal to y naught. Why? Because x1 is not in the first open ball. Since it is not in the first open ball, x1 is not in any open ball. All right, so this is true. Therefore, and then in the second open ball, what do you have? In the second open ball, what do you have? y3 is not there. Why in the third open ball, y4 is not there, like that. Okay, so that means what? In general, what is the conclusion? Xn is not equal to y naught for all n greater than or equal to 1. Okay, it's okay now. Xn is not equal to y naught for all n greater than or equal to y1. So the fact is that, let me explain it again. Y naught is a member of each open ball. Okay, but the first sequence x1, x2, x3, the first element is not a member of the what? The first element is not a member of the first open ball. Therefore x1 is not equal to y naught. Okay, the second element x2 is not a member of the second open ball. Okay, second open ball. Where is second open ball? Second open ball is radius y3 and center at y3 and radius epsilon 2. In that open ball, by our construction, x2 or x2 is equal to y2 is not a member of that open ball. So in that open ball, y naught is there, but x2 is not there. Therefore x2 cannot be equal to y naught. Okay, in the third open ball, what you have done? The center of the third open ball is what? y4, and the radius is what? Epsilon 3. Okay, by our construction, in that open ball, y3 is not there. All right, y3 is not there. Okay, so then, but in that open ball, y naught is there. So in that open ball, x3 is not there. Okay, so in that open ball, what do you have? X3 is there. X3 is not there, but y naught is there, but so x3 is not equal to y naught. So like this, in every step, in nth step, okay, xn is not there, but y naught is there. So xn is not equal to y0. Okay, so now we are able to find out an element y0 of E which is not equal to any member of xn any member of xn. It is not equal to x1, y0 is equal to x1, y0 is not equal to x2, y0 is not equal to x3, like that. So what does it mean? By our assumption, every member of E is also member of the sequence. Every member of the sequence is also member of E. That means the sequence is exactly equal to E. So since y0 is a member of E, y0 must be equal to some xn. Okay, but by our construction it says that xn is not equal to y0 for any n. So there is a contradiction now. In one way it says that y0 is a member of E. In another way it again says that y0 is also not a member of E. So there is a contradiction, this is a contradiction. This contradiction arises from our assumption that E is countable. So that assumption is wrong. Therefore E must not be countable. Okay, that is, hence E is not countable. So that must I want to give that must here only.